starts back in 1929 when the great astronomer Edwin Hubble realized that the distant galaxies were all rushing away from us, establishing that space itself is stretching, it's expanding. Now, this was revolutionary. The prevailing wisdom was that on the largest of scales, the universe was static. But even so, there was one thing that everyone was certain of. The expansion must be slowing down. That is, much as the gravitational pull of the Earth slows the ascent of an apple tossed upward, the gravitational pull of each galaxy on every other must be slowing the expansion of space. Now let's fast forward to the 1990s, when those two teams of astronomers I mentioned at the outset were inspired by this reasoning to measure the rate at which the expansion has been slowing. And they did this by painstaking observations of numerous distant galaxies, allowing them to chart how the expansion rate has changed over time. Here's the surprise. They found that the expansion is not slowing down. Instead, they found that it's speeding up, going faster and faster. That's like tossing an apple upward, and it goes up faster and faster. Instead, the right question to ask is, why do we humans find ourselves in a universe with the particular amount of dark energy we've measured instead of any of the other possibilities that are out there? And that's a question on which we can make headway, because those universes that have much more dark energy than ours, whenever matter tries to clump into galaxies, the repulsive push of the dark energy is so strong that it blows the clump apart and galaxies don't form. And in those universes that have much less dark energy, well, they collapse back on themselves so quickly that again galaxies don't form. And without galaxies, there are no stars, no planets, and no chance for our form of life to exist in those other universes. So we find ourselves in a universe with the particular amount of dark energy we've measured simply because our universe has conditions hospitable to our form of life. Which means in the inflationary theory, the Big Bang giving rise to our universe is likely not a one-time event. Instead, the fuel not only generates our Big Bang, but it would also generate countless other Big Bangs, each giving rise to its own separate universe, with our universe becoming but one bubble in a grand cosmic bubble bath of universes. But because the expansion is speeding up, in the very far future, those galaxies will rush away so far and so fast that we won't be able to see them, not because of technological limitations, but because of the laws of physics. The light those galaxies emit, even traveling at the fastest speed, the speed of light, will not be able to overcome the ever-widening gulf between us. So astronomers in the far future, looking out into deep space, will see nothing but an endless stretch of static, inky, black stillness. And they will conclude that the universe is static and unchanging and populated by a single central oasis of matter that they inhabit, a picture of the cosmos that we definitively know to be wrong. Now, maybe those future astronomers will have records handed down from an earlier era, like ours, attesting to an expanding cosmos teeming with galaxies. But would those future astronomers believe such ancient knowledge? Or would they believe in the black, static, empty universe that their own state-of-the-art observations reveal? I suspect the latter, which means that we are living through a remarkably privileged era when certain deep truths about the cosmos are still within reach of the human spirit of exploration. It appears that it may not always be that way, because today's astronomers, by turning powerful telescopes to the sky, have captured a handful of starkly informative photons, a kind of cosmic telegram, billions of years in transit, and the message echoing across the ages is clear. Sometimes nature guards her secrets with the unbreakable grip of physical law. Sometimes the true nature of reality beckons from just beyond the horizon.